So if you're in the Python shell and you're curious about the type of a variable, the type of anything, you can just use the command type, the function type, and then pass something in between the parentheses and it'll tell you. I mean, some of them are really obvious. We've been talking about strings and floats and things like that, so we can use that to verify our suspicion. What is the type of the number 1? It's an int. What is the type of 1.0? It's a float. What's the type of something with quotes around it? It's a string. What if we use apostrophes rather than double quotes? Does that make a difference? Well, say you didn't accidentally hit enter like I just did. It's also a string. So in this language, it doesn't matter whether you use double quotes or single quotes. Some languages do use those to mean two different things. What about something strange like the type of that? Okay, so print is a built-in function or method. One textbook we used one semester called built-in functions BIFs. Built-in function, I think that's kind of absurd. I'm not going to use the term BIF again. So let's see, what else could we find the type of? A keyword. I wonder if that'll work at all. What is a keyword? Def. Nah, okay. So you can't do that because the keywords define language. They cannot carry a value. One thing I want to point out, I think I've done this before, but if you accidentally use one of the purple words, one of the built-in functions as a variable, it replaces its functionality so that you cannot use it for which it was previously intended. For example, if I say print equals 3, okay, great, now print is equal to 3. Can I print something anymore? No, I cannot. It does not know what's going on anymore. It's easy to fix. I just close the shell and bring it back, you know. But in your program, you know, you would either know right away if you had made that kind of mistake or not, because your program would suddenly stop working whenever you called a print statement or something like that. So a variable is something that can contain a value. Message is equal to what's up, doc. N is equal to 17. Pi is equal to 3.14. So we know that message is a string. What is N? It's an integer. It's an int. And so pi is a floating point number. A single equal sign is called the assignment, whereas double equals means comparison, equals. So you use double equals when you're doing if statements and when you're doing while statements. Single equals everywhere else. So variable names. We try to give variable names. I mean, a variable name is the name that you give to your variable so that you can figure out what it's going to be containing. You know, so that when somebody's reading your program, they understand what your program is trying to do. Because if a program, you know, just does things like x is equal to 1,000, b is equal to 31.5, you know, and then c is equal to 12.7, and then later on, it uses those values, you're not going to really know what those mean. Maybe the programmer was nice enough to put some comments, but the code is a lot easier to read if it says something like, you know, pay is equal to 1,000. Age is equal to 31.5. And you don't really have to type this. These are just examples. You know, and tax rate is equal to 12.7. Something like that, you know. If you use variable names that are descriptive, it makes your code a lot easier to understand. It makes it a lot easier for somebody else to look at it with you, for somebody to take over the programming when you stop on it, for your long-suffering professor to grade. Try to pick good variable names. Single letter variable names are pretty bad. The only reason I use them is because they're simple for us to type in here. And when we're trying to get 25 people all typing the same thing, you know, sometimes I veer on the edge of not choosing good variable names. And usually the longer the variable name, the better, although there could be, you know, some patience temperature measured in Celsius. Yeah, okay, fine. That's a bit much. We don't need to go that far. So we can use underscores in order to try to make our variable names. That's one thing that people do, like that. The other is that they use something called camel case, which is when they use mixed case, uppercase and lowercase, to try to make things easy to read. Patient's temperature measured in Celsius. Okay, you know, there are two different ways of naming the same variable with the same absurdly long name. Nowadays, this seems to be the preferred style that most professional programmers and most textbooks teach. A while back, that was the style. I don't care which one you use. So there are some rules to what you can name your variables. They can't start with a number. So you can't do 1987 tax rate. That's a bad variable name. You can't put spaces. So you can't say tax rate is equal to 30. There's only a few symbols you can use. You can use dollar signs and you can use underscores. I'm not even sure about the dollar signs. Let's try that out. Go back into the Python shell and say a dollar sign is equal to 3. Nope, not in this language. In C and in Java you can use dollar signs. So really you can't get away with using special symbols in your variable names. If you want something that looks like a space, instead use an underscore. So variable names can consist of letters, digits, and underscore. You can mix uppercase and lowercase. But it's very case sensitive. If you do this, apples is equal to 3, and then later on you do print apples, you're going to get a syntax error because you did not capitalize it the same way every time. Generally, that's one argument for making them all lowercase all the time, so you don't even have to think about it. Error because case sensitive. Because case matters. Python and most other programming languages are all case sensitive. You'd have to go back to the 70s to find languages that weren't. Then there are the keywords. You cannot use a keyword as a variable name. It's not one of those things where it'll overwrite the value of it like it would with a function. It just flat out won't work. So if we've talked about the if command. If I tried to type something like if is equal to 3, that's just a syntax error. Completely alien to it. It does not understand what we're trying to do there at all. If has a very specific meaning, and we're not allowed to use it for any other meaning whatsoever. So where are our rules? Can't start with a number. Can't have any spaces. They're case sensitive. Cannot be a keyword. And they consist of letters, digits, and underscores. Okay, so kind of just going to make up some, and you're going to tell me if they are good variable names or not. I don't know if this person is 3 inches or 3 feet tall. This is kind of strange what I'm doing here. Maybe we're out of vet. Alright, besides the fact that these are all silly values that we're assigning there, which of these 5 variable names, more than one of them is incorrect? Which some of these are incorrect?
The 4th one.
That one's certainly bad. Right. And so is number 3, because it's got a space in it.
The 5th one.
5th one's okay. Yep, that one's okay. We're allowed to have numbers in it. They just can't start the variable name. Pardon me? Right, the cases are different. That's dumb, but it works. If you did this, patient height is equal to 3, and then later on you did if patient height is equal to 3, but you capitalize the H, it wouldn't work. But you can use those. Either one is a valid variable name. Just like you could say x is equal to 3, or you could do x, capital X is equal to 3. Those are both totally valid variable names. You just kind of have to pick one, though, and go with it. So that's a valid. This is valid, but it's a really bad idea to have 2 different variable names that look the same in your code. If you ever want to get somebody, you know, a coworker extremely angry with you, you start mixing up lowercase l's and 1s. Like value. There you go. Stick a 1 in there. Okay. Nah, you're not going to do that. Also, O's and zeros are hard to distinguish, so you just need to, you know, use some sense. Programmers choose names for the variables that are meaningful to the human readers of the program. They help the programmer document or remember what the variable is used for. Beginners sometimes confuse meaningful to the human readers with meaningful to the computer. They'll think that because they call it a variable average or pi, that somehow magically calculates the average, or that Python knows that pi should be that. No, the author feels very strongly about that and put an exclamation mark on it. The computer doesn't understand what you intend the variable to mean. It doesn't care if you name it in Klingon or Elvish or Dwarvish or whatever, you know. So you'll find that some instructors deliberately don't choose meaningful names when they teach beginners. Not because they don't think it's a habit, but because they're trying to reinforce the message that you, the programmer, must write the program code to calculate the average, and you must write an assignment to give it pi. Okay, I'm not going to do that. I'm not going to turn around and just because I don't want you to think that pi is a magic word, instead I'm going to decide that I'm going to have a variable called x1 and set it to 3.14159. If I'm going to set something to 3.14159, I'm going to call it pi. So a statement is an instruction that the Python interpreter or the compiler of the language that you're using can execute. There are statements such as while statements, for statements, if statements, import statements, and all sorts of other kinds. If you type a statement on the command line in the shell, Python will execute it. Evaluating expressions. What is an expression? It's a combination of variables, values, and operators and function calls. So it's a series of things separated by operators. The operators being the plus and the minus and the multiply and divide and things like that. Expression is a series of symbols, including variables, values, which are, things like 3.14 or, something in quotes or whatever you type, operators, like that. So here's an example of an expression. 3 plus 4. 3 plus value. There, I snuck that 1 in there just to be annoying. Okay, so 2 times 3 plus 4 divided by 5. You know, these are all expressions. The simplest expression is just something like that. 3 all by itself is an expression. Don't normally think of it as an expression, it just looks like a number. But an expression is a series of at least one value or variable or function return value. So, at least one variable value or function return value. And then if there's more than one, they're separated by operators. So is this an expression? No, because there's no variable, there's no value, there's no function in there. Is that is pi an expression? Yeah, assuming we've defined it. So you can pop open the Python shell and enter expressions, and it will go ahead and calculate them. All right, I want to know what 40 times 99 is. Neat. I want to know what 4 to the power of 1,000 is. Whoa, cool. Alrighty. Most languages don't support numbering schemes that support values that large. It's pretty interesting that Python does. Any expression can be stored in a variable name. Let me start it again. So I could do that 4 to the power of 1,000. I could store the results in a variable named A. Then if I want to print A, I can. There it is. So the results of expressions are stored in variables or used in if statements or as function arguments. I could do print 3 plus 3. 3 plus 3 is the expression. Print is the function. A is equal to 3 plus 3. 3 plus 3 is the expression, and its result will get stored in A. So there are two types of division operators that Python supports. One is called floor division. If you do this, let's do 4 divided by 3. 4 divided by 3 is 1.3333. But if I use 2 slashes, it rounds the result down. Not all languages, in fact a great many, do not have the floor division operator. Let's do a couple of those. 9 divided by 5 is 1.8. 9 floor division 5 is 1, because 9 divided by 5 rounded down is 1. Negative 3 divided by 2 is negative 1.5. Negative 3 floor division by 2 is 2. It rounded it down and went down to the... Kind of counterintuitive to me that it's negative 2 rather than negative 1, but okay. Yeah. When they say they round it down, they really do. So that's floor division. Floor division just means do the math, but then the answer is going to be an integer because it's rounded down. So let's write out our operators. Addition, subtraction, multiply, divide, but 2 slashes is floor division, which means round down the answer. And then there's star star, which means exponent to the power of. So maybe in junior high or grade school or whatever you learned the mnemonic PEMDAS. Please excuse my dear Aunt Sally. What this defines, or it's supposed to help us memorize, is the order of precedence for operators. Parentheses are at the top of the heap. Anytime there's a parentheses in the expression, they get done first. Anything that forces the evaluation of that to be done first. And then exponents. And then multiplication and division share that priority. So multiply, divide, floor divide. And then addition and then subtraction are the lowest priority. So what does that mean? That means that if you do A is equal to 4 plus 3 times 2, that if you just type this into a calculator, you'd type 4 plus 3, hit enter, it'd say 12, times 2, you'd hit enter, it'd say 24, but that's not really what it is. And if you have, a slightly more expensive calculator than the $5 cheapest one, then instead you would type the whole phrase in before hitting enter. And the way that it would get evaluated is that multiplication and division happen before addition and subtraction. So it would get evaluated as though the expression were this: 4 plus 3 times 2. So 3 times 2 is 6, plus a 4 is 10. That's how that gets evaluated. B is equal to 2 times 3 plus 4 times 2. Or divided by 2. Make it easier for my brain. Okay, so out of all these operators, we have additions, we have subtractions, and we have multiplication. Multiplication and division are higher priority than addition and subtraction. So this is going to get evaluated before the plus. Now when you're talking about the same level of priority, then it just gets happen left or right. Like if you have priority mail, the truck still has to go, from one house to the other, down the street in order. But this is going to happen before that, absolutely, and this is going to happen before that, because addition and subtraction are the lowest priority, the lowest precedence. So what does this get evaluated to? 2 plus 3 is 6, and 4 divided by 2, wait, what did I do there? 2 times 3, 6, plus 4 divided by 2. So I think that comes out to 8. We can find that out. We can type that into the shell. Yeah. So that should make sense. We've done that, in eons past in grade school. So you just have to kind of remember that. And if something ever looks funny to you and you're not sure about the order in which things are going to be resolved, go ahead and use parentheses to force the issue. Even if you know that it's correct, if you just want to make it clear. There wouldn't be anything wrong with writing this expression here as this if you thought it made it easier to solve. So let's do a couple. Okay, so what does x equal? In this case, it wasn't a rhetorical question. Somebody tell me.
7.
It equals 7. Why? Because multiply happens before addition. So that's really 6 plus 1 is equal to 7. What about this one? 1 plus 2, excuse me, 1 times 2 plus 3. What? That one evaluates to 5. 1 times 2 is the first part of the expression, and then 3 gets added on. And it wouldn't matter if it was reversed, you know, if you said 3 plus 1 times 2, it's still the same thing. It's the multiplication happens before the addition. How about that one? 3 to the power of 2 is 9, multiplied by 1 is 9. So I kind of goofed by making that 1 by, because no matter how you evaluated it, it would have been the same thing. So I'm going to change that. So anyways, 3 to the power of 2 is 9. 3 times 3 is 9. Times 2 is 18. Parentheses can be used to change the order in which these things are done. Here we had x is equal to 1 plus 2 times 3. What have we had? You know, r is equal to 1 plus 2 times 3. Well, parentheses happen before multiplication and division. So that forces that to get done before that. So what does that resolve to? 9. Yep. I should probably assign a quiz or something to burn that in. Just be warned that there are going to be questions on an exam about that, where I give you some simple expressions like that and want you to be able to evaluate them. There's another operator which we did not see up here, modulus. Have we talked about modulus yet? Okay, I don't think so. Along with all of these guys, plus, minus, times, and division, there's also modulus, which means remainder. So if you have 4 floor division by 2, 2 goes into 4 evenly, so that equals 2. If you do 4 modulus 2, that means 2 goes into 4 how many times? What's the remainder? Well, it went in evenly, so there was no remainder. What if it was 5 floor division 2? That equals 2. 5 divided by 2 rounded down is 2, but it's not even. It had a remainder. So 5 modulus 2, what was the remainder? 2 goes into 5 2 times with a remainder of 1. Somebody always wants to say 0.5, and I feel you, but it's 1. And we know what the remainder means. We're going back to grade school. Modulus is just the operator that that produces that. So if you have, you know, 5 floor division by 3. 3 goes into 5 how many times? That's 1. But it's not an even division, so we get a remainder. So 5 modulus 3 is 2. Are we all? I don't know why I held up 4 fingers. I am not a crook. So anyways, there we go. Are we clear on that? So you can use that to see if a number is evenly divisible. Yes?
I think you answered my question. I was going to ask what was the purpose of the module.
Good, very good question. And why would you do this? I'll give you a few examples maybe. But here's one. Check if x is even. If x modulus 2 is equal to 0, then x is even. Now, how many times do you really care if something is even or odd? Not that many times. So that's not, you know, the end all be all. But here's a better example. Say you have 5,432 pennies or cents, and you want to convert that to dollars and pennies. So dollars is equal to 5432 floor division by 100. I think I'm just going to cut that down to 432. So dollars is equal to cents divided by 100, and then the pennies is equal to the cents modulus 100. So when we're done with this, if we started off with 432 cents and we say dollars is equal to cents floor divide 100, well, what's 432 divided by 100 rounded down? Yeah, so we have $4. After we take $4 out of this thing, how many cents are we going to have left over? We're going to have 32. So so 432 modulus 100 gives us 32. I'm going to change that cents back to 432. It's clearer with numbers rather than variable names. So order of operations, PEMDAS. A few of the operators work on strings as well as numbers, but not to do math. If I say A is equal to hello, and then I do print 3 times A, hello, hello, hello. Do you ever need to do that? That multiplication is pretty silly. However, using the plus sign is important. You do this a lot. You know, first name is equal to Joe. Last name is equal to Bob. Full name is equal to first name plus a space plus a last name. And so full name is equal to Joe Bob. Using the plus sign on strings is called concatenation. So while this is a cute trick, I guess you could like make a string that was, if somebody asked you to print out 10,000 asterisks, you could do that pretty easy. 10,000, or not asterisks, let's pick a 10,000 A's. Yay, alrighty. So anyways, multiplication works, but it's the addition that's important. So string operators. If you have 3 times wow, that equals wow, wow, wow. If you have hello plus world, that makes hello world. You kind of wish there was a space in there, but that's all right. This is the important one, and this is known as concatenation, and you'll hear me use that term more often. So the plus symbol, the plus operator, will concatenate two strings together. Why did they come up with such a complicated word when it just means join? I don't know. But anyways, so that's what it means, join. Technically speaking, you can't say that it adds two strings together because hello and world are not numeric values upon which you can do math. So you cannot add hello to world, but you can join them together. You can concatenate them. So input. They're using a different development environment than we are. If you type this in is equal to input, please enter your name, and it pops up this cool little window. We don't get that cool little window. But we have seen that if you use the input statement, what it does is it prints the prompt and then lets the user type in something, and whatever they type is then assigned into the variable on this side. Okay, so composition. Composition is when you look at an algebraic expression and you turn it into programming code. And what do I mean by that? If you look, in textbooks and stuff like this, they'll say things like area is equal to height times width, something like that. That doesn't work in programming. We would have to multiply those things together. We would have to do that. Or, the area is equal to 2 pi, no, that's circumference. Like that. Maybe they'll be nice and maybe they'll put spaces in it, but you know the way that those books are written, they don't put the big old X in them, once you get out of grade school or whatever. They just expect you to know that if they're putting things side by side, we are supposed to multiply them. We would have to rewrite that as C is equal to 2 times pi times R. What's another example? If we do this, X is equal to 3 plus 2 over 5 minus 3. And we want to solve for that. That's our expression. That's our algebraic formula. Here's what we can't do. This would not work. So composition is taking algebraic formulas and encoding them so our computer can understand them. Here's what's wrong. X is equal to 3 plus 2 divided by 5 minus 3. Looks good. I took the 3 and the plus and the 2 and I did the division and I did the 5 minus the 3. What is wrong with that? Yeah. Precedence, the PEMDAS tells us that division happens before addition and subtraction. So, when the computer looked at this expression, it would go, oh, I'm going to do this part first. 2 divided by 5. Okay, cool. And then I'm going to add and subtract. That's completely wrong. So to fix that, we have to put parentheses in the right place. Scrolling past. Okay, we're at the end of the chapter. Woohoo. Assignment statement. An assignment statement is one that gives a variable its value. N is equal to n plus 1. That would take n, add 1 to it, and store it back into n. There's a shortcut for that. The single equal is called the assignment. This text is calling it a token. Double equals means comparison equals. Composition is when you combine simple expressions and statements into compound statements and expressions. Concatenate, two strings joined end to end. Evaluate, that's when the operations are performed in order and that expression is turned into a single value. After we did this math, well, 3 plus 2 is 5, and 5 minus 3 is 2. So 5 divided by 2 is what x would evaluate to, 2.5. Okay, believe it or not, we're going to get to something more interesting in a moment. I know that just stepping through a PowerPoint or a web page can be slightly stupefying, no matter how magnetic the personalities of the professor is. The operators are the symbols. The operands are the values on which the operator works. So if plus is an operator, A plus B, A and B are operands. Operand doesn't mean variable. If you do A plus 2, then A and 2 are operands. Okay, we're going to go to the next one. I guess this is worth doing right here. Do these in your head right here. Crank out, open up a new idle window or idle file or notepad or something, and just tell me what 5 modulus 2 is, and 9 modulus 5 is, and so on. So, open up Notepad and guesstimate those, and then use the Python shell to check them. So I'm going to go to the Python shell. I'm going to do File New. And we have 7 different ones. 5% 2. I'm going to do that one for you. 5 modulus 2. 2 goes into 5 2 times with a remainder of 1. I believe the last one's going to be an error. You can't divide by 0, so I don't see why you could modulus by 0. Yes, sir.
Since on 3 and 4 have the same numbers in them, are they going to have the same order?
They have the same numbers, but they're not in the same order. So, how many times does 12 go into 15? 1 time. And after it's done, what is the remainder? The remainder is 3. How many times can 15 go into 12? 0. And once that happens, what is the remainder? Yeah, 12.
Yeah, I was wondering how that works.
So just like 0 divided by anything is 0, 0 modulus anything is also going to be 0. And just like you cannot divide by 0, if you punch that into your calculator, it's going to cough up an error, then that's an error. What about this one? What is 6 modulus 6? Yeah, it went in there cleanly with no remainder. How about 9 modulus 5? What was its remainder? 4. Yeah. Okay. Hope we're good with that. And then you could double check that by opening the Python shell itself, Python shell, and just typing those things in. I lost confidence in myself. Yep, that's what I had. Okay, here's a fun chapter called Hello, Little Turtles. The idea behind turtle graphics is, imagine you have a little mechanical turtle on the floor that's holding a pencil. And you can tell it to go forward 3 feet, it'll draw a straight line. And you tell it to turn right 90 degrees, the turtle will turn right. And then you tell it to go forward another 3 feet, it'll keep drawing that line. You know, and so you could give commands to it, and it'll draw something on the page. The original turtle was actually, you know, a little mechanical device that did hold a pen and drew on a big sheet of paper. You know, well, we're not going to do that, but there are graphic libraries that do that. So we're going to create some turtle programs, and the reason we do this is because we can actually learn some good programming concepts through these things, not just because it's fun to draw pictures. So open up a brand new idle window, do save as, and whatever you do, don't call it turtle.py. And that's a natural thing to do because it's a program about turtles. So let's just call it T1 for turtle programmer, or our first turtle or something. And the reason why I say that is because that will eventually break it so that you can't get any other turtle programs to work if you name it turtle.py. And the reason for that is because the first line of our turtle program needs to be an import statement. Import, I don't put quotes around it, wrong language. Import turtle. That means that turtle is a library. It's another py script, chock full of code that gives us some functionality. So that's our first line of code. Now we're going to make a turtle. Now the syntax here, the way that I capitalize it and put the parentheses on at the end has to be exact. I'm going to call this turtle Leo, Leonardo. Leo is equal to, we are creating a turtle from the turtle library, so type lowercase turtle dot uppercase turtle parentheses in parentheses. It probably would not break it to put the spaces there. Let's find out. Okay. So what that means is that this is a function that creates a turtle object. An object is a more complicated variable. An object is a variable that not only has data but has functions attached to it. And what do I mean by that? Leo.forward. Forward march. Go forward 100 pixels. And then Leo's going to turn right 120 degrees. And I'm just going to copy those two statements and paste them because I want him to do that 2 more times. Who can guess what it's going to draw? Square's a very good guess. It's a triangle because a triangle has 120 degree angles. Yeah. If you want the turtle to go very, very slowly, you can add a speed command. Eventually you get annoyed at how slow he is going anyways, and so then you'd add a speed command, but to speed him up. So I'm going to go ahead and list the two speed commands up here. Leo.speed of 1, that would make the turtle as slow as possible. And then Leo.speed of 0, this is kind of contradictory, is as fast as possible. That looks weird, but if you give it higher numbers, it gets faster and faster and faster, but no speed is as fast as putting 0 there. So you could do speed 9 or speed 4 or whatever, you know, and that would speed it up or decrease it. But basically I figured that those are our two favorite values, slow as possible or fast as possible. Yep.
Wait, if we put them both up there with both of them in the Python, wouldn't that make it a syntax error or something, since one's fast and one's slow?
Well, it's like telling somebody to sleep and then wake up. It does it in order. The first thing it does is it sets the speed fast, and then it sets the speed low. So it's not a syntax error, it's just dumb. We shouldn't be telling it different commands and setting it to different states, you know, one after the other without doing anything with it, but there's nothing wrong with doing it. I don't know if I answered your question. A syntax error is one that actually will not run. That produces an error on screen when you run it. And there's a difference between syntax error and dumbness. You know, dumbness are logic errors. And it doesn't break it. But I am going to comment out the fast one. I'm going to put a £sign in front of this Leo.speed 0 just so I can watch it go as slowly as possible until I stop being entertained by it. Yeah. Here we go. Excuse me. Turtles are fun, but the real reason of the chapter is to teach ourselves more Python and to develop our theme of computational thinking, thinking like a computer scientist. We're going to actually hit a lot of cool topics with turtles as we go along. So our first turtle program, they added a couple of extra ones. Added a couple extra commands in here that I find are superfluous, so I didn't put in there. But this first command that they have creates a playground for the turtles. Why you would do that is you could specify how big of a window you want. You could say turtle.screen 80 by 80 and then make a little small 80 by 80. Or if you did turtle.screen 800 by 800, it'd be a great big one. I just accepted the default size, and so I didn't bother doing that. Then we created a turtle. This author named their turtle Alex. They sent Alex forward 50 pixels. They turned Alex left 90 degrees. They sent Alex forward another 30. And then they did this main loop thing, which just causes the program to wait until somebody clicks on the close. And again, we can get away with not doing that. What do I mean by that? Well, if I run my program here, it hangs out and waits here for the window to close anyway. So the only thing, I don't see any reason to use the screen commands unless we feel like changing the size of the screen or changing the background color of the screen. So the first line tells Python to load, they're calling it a module, a library called turtle. It brings in some new data types. Not only do we have ints and strings and floats, we have a new data type called turtle. It's a very complex data type. Why do I say that? Because you're tracking a lot of information with this turtle while it runs. In order for it to work, it has to know where it is on the screen. So the turtle has an X and a Y position, but it also has a heading. Now in turtle world, 0 degrees is that way. Whereas, you know, in our maps, 0 degrees is up like that. All turtles start off facing to the right, and they call that 0 degrees. But he has to have a heading, he has to have an X and a Y, and he has other things too. There's a command that will change the shape of the turtle from this little Star Trek triangle to, you know, an actual turtle shape or a circle or something like that. More importantly, you can set the thickness of the line. You can set the color of the line. All of those are attributes that are all stored in that Leo variable, or Alex in his example. So let's mess with our turtle a little bit more. The way you change his color is with the dot color function, and the way you change the thickness of the line is with dot pin size. So, going back to our script, after all of that, let's do Leo.pin size is 3, Leo.pin size, Leo.color is equal to red, and let's draw a circle. Leo.circle, I want a circle that is 100 pixels wide, 100 pixels in diameter. Ew, it blew up. I made a boo-boo. The mistake was that the computer doesn't know what red means. We have to put quotes around it. I apologize. I'm getting kind of tired of it going that slowly. I'm going to change that Leo.speed1 to 5 just to add some pep into its step. There we go. And if I'm really curious, I'm going to go ahead and change it to 0 and watch it run at max speed. Full power. There. You can fill shapes. Before you draw something, you do begin fill, and then you draw your shape, and then you do end fill. And I always forget if there's an underscore in begin fill and end fill or not. So it's underscore fill. Okay, so Leo dot begin underscore fill. He's going to begin filling. Now let's draw something. Let's draw another triangle, but instead of making right turns, we're going to make left turns. Leo dot forward 100, Leo dot left 120. Now copy those two lines and paste them twice, and then do Leo dot end underscore fill. And that one got filled with red. You can set the fill color independently of the pin color if you want. And you can do that with a second argument to the color command. If I did red, end quote, comma, beginning quote, blue, then the ink of the pen would be red, but when it did a fill, it would fill it with blue. So I think I'll do that. I'm going to come up to the Leo.color command and add a second argument which sets the fill color. I think I want the guts of that second triangle to be yellow. So I added comma yellow there. Much better. So, kind of a super high-tech Etch-a-Sketch. Etch-a-Sketches, it was really hard to draw circles. If you were going to use this to draw anything more interesting than the kind of stuff we're doing here, can you think of other functions, of other commands that would be useful to give to the turtle? What if I wanted to draw a smiley? I wanted a great big circle, and then I wanted two eyes.
The location of where the eyes would be?
Yeah, you need the ability to reset where he is on the screen to give him new XY coordinates. So that's one. Another, yeah, you don't want him always leaving a trail behind him. Because otherwise, like your Etch-a-Sketch, you draw the circle, and then when you go in there and put the eye, and you put the eye, you know, there's lines connecting everything. There's a pin up command. If you do pin up, it lifts the pin, it stops drawing for the next commands you execute. There's a set X command, which resets the turtle's X condition. So if you do set X, parentheses, -200, the turtle would teleport over here. Now, if you haven't done a pin up, he leaves a line wherever you go. And then set Y. You know, set Y works the same thing. So if you did set X, -200, it'd go here. And then if you did set Y, -200, it would go here. Now, those are absolute values. They're not like forward and back. Every time you told it to go to -200, it would be here. You know, and the -200 on the Y plane is there. And you know what I mean by that. This is the Cartesian coordinates. X and Y, X being horizontal, Y being vertical. Positive numbers being to the right and up, and negative numbers being to the left and down. I don't think we've talked about loops much, but we're going to talk about loops now. What if I want to draw a series of circles that get larger and larger and larger? It might have been nice, actually, if I had done that screen command up at the top so that I could clear the page. I guess it's never too late to start. Let's try it. WN is equal to turtle.screen with a capital S. I think it's clear. This could all be completely gobbledygook. Yep, that did it. Okay, so that erased the screen. Why am I going to do that? Because I'm going to write a loop now that will draw a series of circles. So I need a loop variable. I'm just going to call it X. We're going to start it with a width of 0. It sounds, no, with a width of 10. The first circle is going to be very small. While X is less than or equal to 100, colon, Leo.circle, but instead of giving him an absolute value of 100 or whatever, we're going to pass in X as our argument. And now we need to increment X. If we didn't, it would just keep drawing the same circle over and over and over. You know, X equals 10. We don't want it to draw an infinite number of circles with a radius of 10. Instead, we want it to get larger each time. And then lastly, I'm just going to print a done message down here at the bottom so that we know that it's done. We'll obviously know that it's done anyways, but all right, and there's kind of our time tunnel effect. So if you look at it, you can see pretty clearly what that is, what it's doing. X is equal to 10. Keep repeating these statements as long as X is less than or equal to 100. This is the conditional of the while loop. This is the condition upon which it rests. If this condition ever evaluates to false, it falls through the loop. If this expression was false to begin with, it wouldn't even go into it, just like an if statement. And inside the loop, we draw a circle and then we modify the x value. If you loop based on a variable and you're not changing the value of that variable, it's just going to repeat forever. We could prove that to ourselves by commenting that line out, but it wouldn't be that interesting. Just drawing a series of circles is amazingly fun, but let's see if we can make it even more fun. Being slightly sardonic. Okay, so I think I want the turtle to be small again. So Leo dot pin size 1, making him small again. And I'm going to write another loop. X is equal to 0. In this case, what x is going to be is the direction that he's facing. And we're going to draw a series of circles. He's going to draw a circle and then turn left a little bit. Draw another circle, then turn left. Draw another circle, then turn left, and so on. So, and we want to do that all the way around the circle. So while x is less than or equal to 360, it should just be at less than, but it'll probably work the same. Draw a circle, Leo dot circle, maybe 100, and then turn to the left or turn to the right. 45 degrees, half of a right angle. And then x equals x plus 45. So we drew a flower-looking thing there. How is that working? You know what? I'm going to put a clear above that first one. So wn.clear, just because I want to see the flower, nothing else. I just added that. And I'm going to change the speed back down. Scrolling up. You don't have to do that. Oh. I should have just changed the speed local to where I wanted him to slow down, not for the entire thing. That one's interesting. I'm not sure why we had that little white effect there. But it is looping, and it's going to continue looping as long as x is less than or equal to 100. Draw a circle, then add 10 to x. Draw it again, draw it again. Now we're going to do this part of it. It's going to draw a circle, diameter 100. You know, I don't know what's going on with these little left out parts. I'm not going to worry too much about it. You can see it draws a circle, it turns right 45 degrees, and then it draws it again. And in this case, x is just a counter to make sure that we don't keep, drawing circles infinitely. Why did I set, since we were drawing one every 45, I increased x by 45 each time, just so that we would only draw the right number to completely fill it. So a couple of things about geometric space is that there are 360 degrees in a circle, and that kind of is important for things like drawing triangles and drawing squares. If you want to know the angle for drawing a square, I'm just going to put this in notes. A square has 4 sides, so the angle is 360 divided by 4. A triangle has 5 sides? Nope. 3 sides? Where in the world did I come up with that? So the angle is 360 divided by 3. equal to 120. So we could write loops that would draw triangles or squares. The point of a loop is to shorten the code for a repetitive operation. You know, drawing those 8 petals of the flower, we could do it by cutting and pasting this code, you know, 8 times. This would draw another flower. Don't do this, but, you know, 3, 4, 5, 6, 7, 8. That's what's known as brute force. You know, no looping. We're just going to copy and paste the code as often as we want to get it to work. Loopings make this kind of thing far more elegant. You know, with loops, you know, looping are what computers are all about. You're playing a game, the computer's just looping endlessly, waiting for your input, responding to it, updating its screen, checking the data to see if some winning condition or some losing condition has occurred. Loops can be used to, you know, to calculate. You know, you could calculate the value of pi with a loop. You could calculate, you know, monthly interest over a series of time with a loop. You could write some kind of simulator where you're calculating, you know, where you're updating the data that represents the weather, and the simulator is supposed to run for 7 days to show you whether it's going to rain, you know, on Thursday or not. You know. So these are very simple loops here. These are known as counting loops. You know, we had a variable here, and we just counted until, you know, that variable hit a certain condition, and once that condition was met, then we stopped looping. All right, let's play with loops just a little bit more, and then we'll take a break. I think we've already made our turtle program confusing enough. So create a new program and do save as, and call it loop1.py. Let's write a loop that will add all the numbers between 1 and 10. Now for this, we're going to need a loop variable, a counter, but we're also going to need a total. And I wish I could call my total sum, but sum is actually one of the purple words, so I'm not going to do that. I'm going to write total instead. I have to initialize it to a value. It's going to be our accumulator that holds the total. The reason I have to initialize it is because I can't add on to it later if it hasn't been initialized to begin with. So, and then we need our counter. X, we're going to go from 1 to 10. So we're starting X off at 1, and while X is less than or equal to 10, colon, total equals total plus X, and then X equals X plus 1.
You wrote between. You want to include 10?
Yeah. Yes. So instead of saying 10, I'm going to put from 1 to 10. And then if I wanted to be very precise, I would put inclusive, meaning both ends. And that is not a spurious question. A lot of programming problems are caused by not determining whether it was supposed to stop before it hit that end number or not. And that would be controlled by making it either less than or equal to. And then let's print out X. Nope, let's print out total. Why would we print out X? It's just a counter. So having written this a few times, I bet it's 55. Yeah. There's a formula for calculating the summation. This is a summation loop. Let's write another loop that's going to print happy birthday 4 times for some reason. So X is still our counter. I'm going to set it equal to 4, and I'm going to start subtracting numbers from it, and as long as it's greater than 4, we're going to print out happy birthday. So while X is greater than or equal to 0, no, while it's greater than 0, print Happy birthday to you. And then we still need to modify x. I'm going to leave that step out. And then lastly, there's going to be a print done at the bottom. Now this is bad logic. I did not want it to print happy birthday infinitely. My problem was I have a condition for my while loop that relies on the x variable, but I never change its value. So it has no way of escaping the while loop. So I'm going to do x is equal to x minus 1. Now to just hopefully print it 4 times. I may have goofed and made it do it 3 or 5 times, but hopefully I got it right. There we go. So the general syntax for a while loop is this. You often initialize counters, totals, things like that, and then you do while, and after the while word there will be some expression, which we're going to call the condition. Other languages force us to put the conditions inside parentheses, and that doesn't break Python. So I'm just going to go ahead and leave it like that. And then inside of the while loop is the stuff, the body of the loop that does the useful stuff. And then if your loop involves incrementing or decrementing or changing a variable, then change condition. What I mean by that, you add 1 to x, you subtract 1 from the year, whatever that kind of thing is. That's our general syntax. Everything indented is considered to be under the body of the loop. So to flowchart a loop is a lot like flowcharting an if statement. And an if statement is similar to a loop, but it doesn't cause it to repeat itself. An if statement looks more like this. Int, x is equal to input. What is x? If x modulus 2 is equal to 0, colon, then print x is even. Here we're just checking to see if the number is even by dividing it by 2. And if there is no remainder after you divide by 2, you know it's even. That's an if statement. Great. If it's true, it does that. If it's not true, it skips it. While is kind of like that. If it's true, it does it. If it's not true, it skips it. If I set x equal to -1 right here, it wouldn't print happy birthday at all because x was never greater than 0. But when an x is done, it just falls through. It goes all the way to the bottom. When a while is done, it jumps back up and checks its condition again. So when we draw an if statement, we're going to have a diamond, and we're going to go off to the side and do something, but then we're going to go back to the bottom and keep going down. Whereas with a while loop, we do some stuff, and then we have a line that goes back up to the diamond. So pop open the Lucid chart. Oh, neat. You can draw flowcharts on your iPhone, on your Samsung. That's good to know. Okay. If you don't remember your password, I can reset it. If you don't remember your email address, I can look it up if you come here. I wish that we could all use the same password, but it gets confused. What I mean by that is if we could just have one account, student@rose.edu, that sure would make things easier than having to manage all the passwords. I thought I had already done all this. Alrighty, so every flowchart starts with a start. Let's reverse the order and do that if statement first. You know what? I don't think my code worked. If I come back here and actually ran that loop code, it would break. It would crash. What did I do wrong? I know somebody will spot it. We could run it and find out. Yeah, our input returns a string. It's not a number at that point. We would have to convert it to an int. You know, x is equal to int x. We could probably do a float as well. The idea of doing remainders modulus on floats is kind of an odd idea, so I'm going to just stick with an int. Some languages do not let you do that. I believe Python does. I'm going to actually run it now to make sure that I don't have any syntax errors. Okay, there we go. What is it? If I type in 10, it'll say x is even. Very good. Let's do that part of the flowchart first. We're going to input x. So input done in tilted blocks. I'm going to skip doing the conversion because this is just a flowchart. It doesn't actually have to be, show every step in the universe, because not every language would require you to change that input to an int before you did some calculations on it. But if we wanted to stick that conversion in there, I would put it in a math block, in a process block. Convert x to int. I could put that there. But it's going to just add a block to my screen, make things harder to see, so I'm going to delete that. Okay, after that input x, we had an if statement. If x modulus 2 equals 0. If statements and while statements go in decision blocks. So if x %2 equals 0, and if that's true, we want to print a message. Printing goes in the same kind of block as an input. So print x is even. Now we can't have a dead end. This just can't run off over here because we know that eventually down at the bottom there's going to be a stop at some point. So we need a place for the lines of execution to join back up together. Easiest thing to do is just to grab a circle, maybe shrink it down, maybe take the A out of it if you can and want to, and that just serves as a connecting point. You can get away with not putting the circles and using the next block as a connecting point, but to be more rigorous, that is the correct way of doing it. Okay, so that's a flowchart for an if statement. A while loop is going to be very, very similar, except the line is going to go back to here. Our code did not ask for the upper boundary. It just assumed we were going to 10 when we did, add all the numbers between 1 and 10. We're going to flowchart it a little bit more complex, and then we will go back and code it to allow us to do that. What we're doing is we're going to change the logic of that program that we wrote so that it asks for the top value, So I'm going to scroll over here, start, now what should I call the upper bounds of this summation? Max seems like a great term. Unfortunately, max is one of the purple function words. Stop, end. Top. Top sounds good. So, input top Now we have a top, but we need a sum counter, a total counter to hold our stuff, and we need a loop variable, you know, so that we can add 1, 2, 3, 4, 5.
Why wouldn't that be in a data block?
Yeah, that is in the totally wrong shape. Thank you very much. Spacing out. That goes in a data block. So that's the top of our range that we're going to count up to. Then we need a total variable. So total is equal to 0. We need a counter variable. X is equal to 1. That's going to be our starting point. It's going to go from 1 up to 10 or whatever they enter as top. All right, I'm going to kind of cheat here and draw a line from that one all the way to that one. And then I'm going to right click on that line and do send to back. Arrange, send to back. There. Okay. Just a cheaty way of connecting more than one thing at the same time. If you're used to using drawing programs, you know, you're used to the idea of sending things to the back or bringing them to the front. And you just do that with a right click. Okay, now we're ready for our loop. While, and I'm going to hit Control Enter, Command Enter for the Mac users, X is less than or equal to the top, jut off to the side. Let's add X to the total. Total equals total plus X. And now we have to add 1 to X to get it closer to the top. If you entered a negative number for this algorithm, you know, if you said, I want you to run up to -10, that's not going to work. We could make it work if we went to some considerable effort. It would have to know what it was going to be adding or subtracting 1, you know, to X. We're not going to mess with that. So we need another math block because we're still just modifying. We need a process block, so X equals X plus 1. All of this stuff that's off to the right is stuff that would be indented in the code. So while X less than or equal to top has a colon, you know, everything that's inside the loop would be tabbed over in our program. But this one doesn't go back to a circle. Instead, it goes back to the while. And you wrestle with it to get it to look good. These things can be a real pain to draw. All right, now I need to print the total. So that's going to be the last thing I do. Prints also go in data blocks. Print the total. Or I could make it a fancy print statement. Print, you know, quote, total equals, or whatever, you know, but that's enough. Trust that the programmer is smart enough to figure some things out for themselves if you're making a flowchart for them. And then I need a stop at the bottom. So different textbooks call if statements and while statements different things. These are flow control statements. There's another term. Spacing my mind. What do I mean by that? Because if this is true, flow is going to go that way. If it's false, flow is going to go that way. If this is true, flow is going to go that way. If it's false, it's going to go that way. And you can see that if we never change the value of X, it would just repeat that over and over, which is called an infinite loop. Now there is a keyword that will cause a while loop to exit. It's called break. And we may take advantage of that later. So that's something that looks like an infinite loop, really won't be because it has a break statement somewhere in there that causes it to immediately exit that loop. So things about flowcharts to note. Is it a religion that yes has to go off to the right? No. At least one professor here, Dr. Beyer, likes to make the yes go off to the left rather than the right. I do it to the right just because we start tabbing, you know. Tab at the if statement, tab at the while. Is it religion that has to go top down? No. Is it religion that this no block had to be off the side? Could it go that way? You can draw these any way you want. The closer they look to what I do up here on the screen, you know, the easier it is going to be for me to grade it just because I'm familiar with it. And it'll be closer to what other people expect. You know, what do you do if you hit the bottom of your page? You could make it just keep going on the next page. You could just draw one infinitely long flow chart. Or you could put a little letter A and a letter A there, you know, to show that it's jumped from there to there. Or you can actually draw a line from there to there. Now, I created this as two separate flow charts, whereas in our program, they were actually one after the other. You wouldn't necessarily have. If I was going to implement this the exact way that it was in our code, I think we had a birthday loop. You know, so you'd have start, and then we'd have our birthday loop, and then we'd have our while, you know, our total counter, and then we had the x's even at the bottom. So you could have a column of code and a line hooking it up to the next column, and then a line hooking it up to the next column.
Would there be a start and stop in each one of them, or just at the beginning and the end? Would there be a start and stop on each one of those?
No,
or would it be
no.
just the beginning and the end?
No, it would not. Here's what it would look like if I'd done we're good with understanding that these are actually two separate things, but if we had written them in the same program, here's what it would look like. Two ways to solve this little conundrum. One is you could do that. You could stick an A down there, and you could stick an A up here, and it's kind of like, you know, a teleport block in a game or whatever, you know. That's one way to do it. The other is that you can just draw a line. You could say, okay, that's going to go here, like that. And then you have to mess with it, make it look pretty. I would do this if I was trying to show that these things happened in that order and that it was all one chunk of code. I'm going to undo those changes because the real point of this specific exercise, I think I said specific exercise, is just to make sure you get the difference between if logic and while logic. Most of our programs, our long programs, will be written like that though. They'll have a column of code, they'll come up here, they'll have another column of code, or they may just keep going. And it's up to you how you want to do it. I just have to kind of wrestle with how to put as much on the screen while keeping it readable for y'all. Okay, so I'm going to hit undo a couple times. Get my start and stop back again. If you really care, you can take things like lining these things up carefully. Shift click a bunch of shapes, right click on them and choose align, and you can align them all to the center, and maybe it'll line them up. It still didn't get that stop one right. It seems to be snapping to some grid that I might be able to disable that. Okay, why don't we stop here? You need a bathroom break, get a drink, whatever. We'll hook back up at about 1:55. Okay, there's another kind of loop called a for loop. Very, very similar to a while loop, except it doesn't require any setup in advance. You don't have to define your loop variable. It creates a loop variable on the fly. And I guess maybe that's simpler in the concept of this textbook writer's mind, because this chapter hits for loops and it doesn't hit while loops. So let's go ahead and talk about what a for loop is. Flowcharting wise, it's the exact same thing, except you, in your diamond, instead of putting a while, you put a for. So diamond, shape, for, whatever the condition is, you have some code and it loops back to it. Now for statements in Python can be done one of two ways. And the one way is really kind of funky. I guess we can go ahead and type it. It involves using something called a list. And the other is a range. So we kind of need to distinguish between those two. I almost hate to go this far. I'm gonna skip the list entirely, I think. Yep. Instead, we're going to do range statements. So we've seen while loops. You use while loops to implement repetition of code. Repetition of code. For loops also do repetition. They do it over a predefined sequence, predefined set of values. I guess I will show you the list concept as well. If we did this, for X in, and then we created a list, Joe, Bob, Jack, Janet, and then I did print X. It would print Joe, it would print Bob, it would print Jack, and it would print Janet. What it's doing is it's stepping through this entire list in turn, filling in the value of X with the values in the list, and when it's done with the last value, it exits the loop. So we're not defining, we don't have to initialize our variable up there, we don't have to change the condition. All of that is handled for us. So in some ways, for loops look easier to write, or they're more terse or whatever. Implementing this as a while loop would take several more steps. We could do it. Now, I'm going to kind of not do this again for quite a while. I don't care about stepping through a list like that. Anything between square braces like that, separated by commas, is known as a list. Other languages may call them arrays. Here's how you more commonly see a for loop written, with a range keyword. Somewhere in your massive code, for your loopy stuff, write this. For X in range 10, colon, print X. And then run that and see what numbers it prints out. Okay, it's kind of annoying that it's asking for X and then we're calculating X, but anyways, you see what it did? It looped, printing out all the values between 0 to 9. Here is where your question about whether it's inclusive or not is very important. Because the range statement starts X at 0. You might think it's going to start at 1, but computers start counting at 0, just like homework is 0. And it goes up to, but not including, 10. This really did give us a range of 10 numbers, but it's a range of 10 numbers that starts at 0 and ends at 9. So this number in the range statement is an upper end. It defines 1 past the end. And that's a little bit confusing, or it could be. Kind of wish that if I put a 5 here, it would go up to and including 5, just like I had written. Don't type this, but, or you can if you want to. This is the exact same code here as this. If I did this, A is equal to 0, while A is less than 10, colon, print A. Those two things do the same thing. Oh, but I forgot something. What did I forget in my while loop? Let's run it and find out. Yep. I wasn't expecting it to stop there. I was expecting it to run. Anyways, I forgot to increment A. So it should have just printed out 0 a million times in a row. Like that. That's what I expected. Infinite loop because I forgot. And I do that quite often when I'm writing a while loop. That's why I like for loops. One of the reasons why I like for loops. If it can be expressed as a for loop, it makes the coding considerably simpler because I don't have to initialize A and I don't have to remember to update A at the end. So the range statement lets you specify a beginning and an end and even a step. Like if you want to count from 10 to 100 by 10s or 20s or something like that, you can do that. I guess you can't count from 10 to 100 by 20s. For B in range, I want to start at 1 and I'm going to go up to 20 and I want to do it by 2s. It's going to print out odd numbers actually. So let's make it from 10 to 20 by 2s. Print B. So the very last thing we should see are some numbers that go 10, 12, 14, 16, 18. Again, the way I wish it worked, and it's not the way it works, is I wish it would include 20 in that sequence. But 10, 20, 2 actually generates the numbers 10, 12, 14, 16, 18. It stops when it hits that number. It stops before it hits that number, not after it hits that number. So this is only going to count up to 18, just like this one only counted up to 9. If you get that wrong on an exam, I'm gonna, you'll get partial credit for knowing what a for loop does. But the range, the upper number is not inclusive, speaking mathematically.
I don't understand the syntax of putting 10, 20, and then 2. Like, could you do 2, 10, 20, or why do you have to do it?
Here's what it actually means. For variable in range, start, stop, and then step. This is the starting point. Starts counting at 10. It keeps going up until it hits 20. And every time it updates B, it adds 2 to it. This statement here, for x in range 10, if I wanted to write it the full syntax with the 3 variables, I could have written it like this. For x in range, where does it start counting? We've already established that computers start counting at, come on guys, help me. It's at 0. It's going to go up to but not including 10, and it's going to increase by 1 each time. Does that make sense? Okay, yeah. This is a shortcut for that.
Computers do that thing where if it has a parenthesis, then it's not included, but if it has a bracket, it is included.
That would be neat, but no, it doesn't do that. Very good question. The question was, in math, if it means the bracket means inclusive and the parentheses means non-inclusive. So if we used
For like a range.
Yeah, so if we did that, it would count 10, but it doesn't. The reason it doesn't do that is because the parentheses has a, the square brace has a very specific purpose, which we saw here to define a list. And so we can't define, we can't mix those with the parentheses or use it for a different purpose. Wish it would. You just have to remember to go past. If I want to count from 1 to 100, I would need to do for x in range 1, but go up to 101. I can leave off the step if the step is 1, but I'm going to put it anyways. If I want to count from 20 to 100 to 200 by 20s, I would do for x in range. What's the starting point? What would be a good end point? And there's more than one correct answer, but the incorrect one is 200. 201, 210, 220, whatever. You just got to put one past the stopping point and then go up by 20 each time. You can also count down. We're counting them down. From 10 to 0 by negative 1s. This one I want to actually do to make sure I get it right. For x in range starting at 10. Now if I put 0 here, that's going to be non-inclusive, I think. So I think it's only going to print up to 9. Let's find out. Yeah, it went from 9 to 1, not 9 to 0. So it's annoying that to go from 10 to 0 by negative 1, I actually have to make that one negative 1 just to get it to hit 0. We'll deal with it. How many times do we count down anyways? You know, usually we count up. Okay, so those are for loops, and we're going to hit the topic again. Specifically in using them for something more interesting than just printing a series of numbers. But that's what the range statement does, is it generates a series of numbers. Go back to the shell now. Do run Python shell. Go ahead and close it if you're maxed out at the bottom like I am. Run Python shell. And then just type print, parentheses, range, parentheses, 10. And make sure you have the right number of parentheses because you have to have the same number of closings that you have openings. Oh, never mind. I thought it was going to print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Failed experiment. You can program in the shell if you really want to. We could do for x in range 10 colon print x. But if you make a single typo, it's very annoying. You can't just go back and correct it. Oh, I really wanted it to go to 11. You can't do that. So you don't write your programs in the shell. So let's go back to our turtle program and find a use for the for loop. So T1, go all the way down to the very bottom. Let's write a turtle program that... Somebody send me a text before next class. Hey, we actually have markers. Here's what I wanted to do. I wanted to draw a line. It's not going to have dots on it. Then go back to its starting point. Turn, and then draw another one. You know, like that. That's what I want it to look like. There is a back command along with forward. That would be the easiest way to do it. Forward 100, back 100.
Turn.
We wouldn't even have to, yeah, and then turn left or turn right 45 degrees and do it again. So how many points are there on this guy? 1, 2, 3, 4, 5, 6, 7, 8. Just like the 8 cardinal points of a compass. So we're going to need a range statement. And we want it to count 8 numbers. So we're going to do something like for x in range. And there's more than one correct answer, but somebody come up with one that's going to give me a series of 8 numbers.
Be 360 divided by 8. So.
Yeah, that would calculate the angle. So that's a very good point. Angle is going to equal 360 divided by the number of points, which we could call p. And then if we do this, for x in range p, that would actually accomplish it, because it's going to count from 0 to p minus 1. So if we do p is equal to 8, angle is equal to 360 divided by p, and then for x is equal to range p, it's going to count 0 up to 7, p being 8. But if you count on your fingers, 0, 1, 2, 3, 4, 5, 6, 7, that's actually 8 numbers. So that will do it. Thank you for prompting me that, because that makes it more flexible. We can make, you know, a spiny starfish with 100 points, or something with only 3 points. Let's give that a shot. Let's see if we can remember what we did. Input, or wait, points is equal to input how many points let's convert it to an int. Points is equal to int points. Let's calculate our angle, because it's going to be 360 divided by points. Angle is equal to 360 divided by the points. I think we ought to speed this thing up. I think I have mine set slow anyways. Leo.speed 0 will be the fastest. I think we ought to clear the screen. wn.clear, although that seems to do something funny. It leaves some blank spots. Now we need our for loop. For x in range, counting from 0 to points, if I wanted to do the long form where I specify 3 values, I could put 0 comma in front of it and comma 1 at the end. Don't make it do that, but you know, you could if you feel like being totally obsessive compulsive about it. Range 0 comma, and that's no slam on OCD people, and I tend to kind of be one. 0 points comma 1. You know, it's going to start at 0. It's going to go up to, but not including points, and it's going to increase by 1 each time. All right, now let's draw a line and then go backwards and then turn. Leo.forward. Make this a big star. Go 200 points. Then go backward. By the way, if you want to abbreviate, FD means forward to turtles. I don't know what the abbreviation for back is. I'm going to go ahead and use the left. Yeah. And then let's turn, I don't know. Let's go to the right this time. We've been going to the left a lot. Leo.right by the specified angle. It's possible that'll work. Now the only annoying thing about turtles, besides the fact that I made it go very slowly and I need to correct that, yeah, I need to correct that. Okay. Is that when it asks a question, you're going to have to go back to the shell and type it in there. And you won't even know that it's waiting there for a question. So I certainly need to find where I set the speed slow. Yeah. Get it back to Leo speed 0 for the whole thing. All right, there we go. Now it says how many points. I'm going to come over here and I want 8 points. It says done. I wonder what it drew. See if I can find my window. Oh. Well, that's not pretty. Let's write a separate turtle program because this is getting kind of annoying. Take those lines of code right there that starts with points is equal to input. Copy that. Copy all that stuff. Your favorite way of copying. Right click, choose the edit menu, do Control C, whatever you want. Do new file, save as points, or T2 for turtle, whatever. I'm going to call mine points. I need to make some modifications now. Why? Because it's no longer importing the turtle library. And we no longer have a turtle called Leo, and we no longer have a wn.clear. Honestly, we don't need wn.clear anymore because we're starting from a blank slate. So I'm going to make a few mods to this. I'm going to come up to after we calculate the angle, and let's import the turtle library, and let's make Leo. Leo is equal to turtle dot capital T turtle parentheses in parentheses. And then get rid of that line that says WN clear. Don't need to clear it with We've already started on a blank page. I didn't get to see it draw, but apparently it did. Maybe if I push the shell off to the side and run it, I get to see it draw it. You know what, I should just take the input statement out. That'd be the best thing to do. Yeah. Okay. Final mod to this. Comment out the points is equal to input, and just change it to points is equal to 8, or whatever number of points you want to draw. Like I'm going to change it to 100 eventually. Yeah, that worked, and it even left the window on the top of the screen. Okay, so points is going to be equal to, maybe not 100, maybe 90. You know, like 90 degrees. There we go. Groovy. Hippies used to buy posters, blacklight posters that had wild optical art patterns like that so that they could sit in their bedroom and stare at it while listening to Pink Floyd. There we go. Alright, I can't think of anything else to do with turtles at this point. There's going to be a turtle homework assignment, but it's just going to be typing some code in. We will come back to turtles again when we hit the idea of defining your own functions. And what do I mean by that? I told you about pin up and pin down, but we didn't actually use it. But we could write a single function where you said draw circle at 100, 200, position 100, 200, and I want it to be a red circle, and I want it to be 40. I'm using too many numbers. Anyways, it would lift the pin up, it would go to position 100, 200, it would set the color to red, and then would draw a circle of diameter 40. So then you could use that, you know, to put circles all over the screen with a call to a single function. You call that, you know, and you say, I want a black circle here. It's just one line of code. Boom, puts it there. So you can encapsulate large chunks of code into functions. You do that to make it easy to call them over and over and over. If I wanted to draw these stars all over the screen, I could put this star code right here inside of a function. And then I could just do draw star, and it would do it. And then I could move the turtle somewhere else and call it draw star, and it would do it again. If you find yourself cutting and pasting code for any reason other than because your professor told you to, then it's probably bad programming. You don't want duplicate code. You want your code to be written in such a way that if there were any duplicates, you fix it to use loops, or you fix it to use functions. And what do I mean by that? You don't type this. This would be really dumb. But you know our code that added up the numbers 1 to 10? We could do this. Total is equal to 0. Total equals total plus 1. Total is equal to total plus 2. Total, okay, you know, all the way up to 10. Again, that's kind of a brute force approach, and that's a term that people have used for a long time. It's a completely inelegant way of solving it. Weirdly, there are times when brute force is appropriate, and that's when you're trying to write the absolute fastest code possible. We don't care about writing the absolute fastest code possible because these machines, well, not the ones in this classroom, but, you know, computers run insanely fast. But if we did this, and so on, rather than writing it like this, two ways of writing it, you know, or with a while loop. While x is less than or equal to 3, total equals total plus 3. And there's no reason to be typing any of this in. I should be putting it in comments or on the note page. Why would this be faster than this? Because this requires a check each time. And I forgot to update. You know, should be plus x and then x plus equals 1. You know, something like that. I would have to initialize total. I'm going to go ahead and make it all copacetic here. X is equal to 1. There we go. So these two conceptually give the same answer. These add up the number 1 to 3. This adds up the number 1 to 3. This is by far the most elegant way of doing it, because what if we were going to add up the numbers 1 to 1,000? You would not want to have 1,000 lines of code to do that. But this is called unrolling a loop. Now, if you have a loop, but you need to modify it to run as fast as possible, you try to eliminate it, the while condition, because that takes time. Doing this check to make sure that x is still less than or equal to 3 takes a couple of cycles of computer time. And this was important way back when. Not really important anymore. Nobody does this kind of thing in preference of doing this. But if you're doing assembler programming at the very lowest level of programming for some, kind of underperforming chip, and it needs to eke out the max performance possible, then you start coming up with alternate ways of programming where rules like put everything in a function no longer apply, because making a function call takes time. It's got to jump to a specific point in the code. It's got to remember where that code is, and then there's got to be a return statement that sends it back down to where you are. That takes time as well. Okay, enough philosophizing. I'm just going to put in our notes, avoid duplicate code if you can put it in a loop. Later on, we will also avoid duplicate code by putting it in functions. That we will do on Wednesday. So homework assignment based on this stuff. One is I just have a little bit of programming that I want you to enter. And yeah, I stole it from the page that we've been looking at. Just run it and watch it and try to figure out what it's doing. It does a couple of things that we didn't do. It sets the background color of the screen to be pretty. It changes the shape of the turtle from the little triangular chevron, whatever it's supposed to be called, to an actual turtle. And then it uses a command called stamp. What stamp does is it actually would, like a rubber stamp, boom, it puts a turtle on the screen right at that spot. It keeps that thing there. So I want you to look at this range statement, just kind of figure out what the code is doing, why it does what it does, just to understand it. So you're going to enter this in, get it to work. That's pretty easy to do. It's just, there's no logic involved there. Here's a different program. This is part 2. So call that one test.py. And then call this one mathstuff.py. Write a program that asks the user for two values, x and y. Have it print the following calculations. Have it print out what x plus y is, what x minus y is. So when you run the program, it's going to look something like this. What is, come on, go to the next there. What is x? And say you type in 10. What is y? Say you type in 5. Now, x plus y, this is what it could do. And this, you'd get partial credit for this. Partial credit. X plus y is 15. X minus y is 5. X times y is 50. X divided by, x to the power of, and so on. I don't even know what 10 to the power of 5 is. Yeah, I do. I think it's that. 1, 2, 3, 4, 5. And so on. This, why is this kind of lame?
Well, it doesn't tell you what it is.
It's not telling you what it is. Better is to do this. X plus y, or even x plus y equals x minus y, x times y. That's a way better program. Even better. So I'm going to have to go back and copy and paste because I did not. Even better would be if it printed out this. What is x? 10. What is y? 10 plus 5 is 15. If you can't get it to do that, that's fine. But if you do get it to do it, you'll get extra credit. Wait, so this was supposed to say extra credit. And so on. And it's supposed to do more than go up to the exponent, you know. It's supposed to actually do all of the operators we've seen. Addition, subtraction, multiplication, exponent, division, floor division, and modulus. So actually have it use input statements. Don't just make it say x is 10 and y is 5. So use input statements. Partial credit is just going to print out a series of numbers like this. That's lame, so y'all aren't going to want to do that. What am I doing? I don't know. I had all this in and I overwrote it. I wish I kept it. Okay. All right, that makes sense. 2 programs. One is just the, you know, the type in what you see and run it and try to understand it. More of a think piece. The other is actually to do some work.
So it's full credit or you change it back to partial credit.
Thank you. I'll make the assignment look prettier. Alright guys, let's go ahead and end. That way if you have questions over any homework that you've already done, we can hang out for 15 minutes or whatever, or if you want to stay ahead and...
For example, I cannot get this loser chart uploaded to the Dropbox.
Okay, I'll help you with that. So, we have Dropboxes for some of our stuff that we did. Specifically, we drew a flow chart, I recall. And we did some turtles. T1.py and points.py. And then we did some loopy stuff. I forget if I called it loops or loopy or whatever. And honestly, I'm not going to count you off if you don't get all 3 of those in there. Like if you can only find one of your turtle programs other than both, that's okay. And let's upload the homework assignment.
Do you want us to upload the composition from the text file, or were we supposed to even type that out?
When I type in a text file, I'm making notes. It's totally cool for you to be making notes, and if you want to upload them, that's cool. Not required. Test.py, which will be enigmatic unless you look at the program and realize that he called his turtle tests, and math stuff.py. And that's due on Sunday night.